All right. So today's going to be a little bit out of not the usual lecture, so it's going to be some sort of pictorial introduction into what's going to happen next. And I want to say that this, of course, is this would be any enumerative geometry and its relation to with integrable, kind of integrable theory, integrable system is a very, very complicated subject, very deep and multidimensional. I'm going to just present one view of it. It's not only a very personal view, but also very much dependent on where on the coordinate system of this course, where this course is going, what are our goals, what have we learned so far. But this would be anyway. But it is a point of view, and I'm not suggesting you take this point of view, but I do want to say this, that any kind of human activity always develops a certain framework, a certain collection of stories around it, and you should develop kind of your own vision. You absolutely don't like I said, you have to based on you have to develop your own view of the field based on knowledge, based on critical thinking, and not repeat what I say or not repeat what other people say without thinking about it. So this is this is going to be slightly different from the usual things. Anyway, so this is the way this course is set up. Our goal is to understand some aspects of the theory of membranes and M theory. And in particular, that is the way they manifest themselves via the connection between M theory and DT theory. And so this is, and then, but then there is a bridge to GW, that is to say the Gromov-Witten, and this is the Donaldson-Thomas Gromov-Witten correspondence. And then in the world of kind of Gromov-Witten counts, there's a lot of work, a lot of different approaches to how to see various integrable systems and so on and so forth. And this is a huge, like I said, this is a huge. It's only so the picture is obviously the picture is artistic rethinking of a classical picture by Saul Steinberg, and this Saul Steinberg's point of view was to illustrate that New Yorkers have this kind of limited viewpoint where two avenues of in New York City take about as much space as all of United States, about as much space as all of Pacific Ocean, and much more space than India, China, and Russia combined. This is what are the countries on the horizon. And similarly, we will, from judging from where we sit now, all the different connections between Gromov-Witten theory and kind of the great plane of solitons, or the great planes of solitons equation. They all kind of they're slightly they're not what we were they're not. Somehow they look a little distant from this point of view, but anyway, this is a point of view, and I'm going to explain that. And maybe rather than starting from M theory, let me actually work in this talk. Let me work my way from the most distant rock we can see in this picture. That is the KdV equation, and that's where we'll start. And so there's some other pictures we're going to use in this talk, and we'll come back to them later. And so, right. So, so the classic kind of when people talk about enumerative geometry, they really usually mean this. You have like I said, as I understand it, indicated on the previous picture, that this usually means you have some intersection theory on some moduli space of geometric objects, such as maybe the Grassmannian, maybe doing Schubert calculus, or another moduli space that people really like is this M G N bar. This is the Deligne Mumford moduli space. of stable pointed curve. So stable pointed curve, well, it's a it's a curve. May have nodal singularity. So let me draw a nodal singularity, and then it has n mark point. So maybe would be genus equal to 4. The number of points is equal to 3 here. And so, and the cohomology of that space is very interesting, very complicated. But if you're asking for the ones that is stable in G, that is somehow something you can define for kind of infinite genus, then there was a conjecture of Martford proven by Madsen and his collaborators that in fact there's the classes that are stable are the following ones. And so you can think of so you can people. So if you have the nth mark point, maybe call this mark point P1, P2, Pn. So if you have ith mark point, then you have T, the tangent line at the mark point to my curve C. That's a line bundle. That's a line bundle. You can take the dual one too. So this is a line bundle. Over this moduli space, and the all the cohomology classes that we're going to consider, that the stable ones, they come from Chern classes of this bundle. And so and then maybe people the way to organize this is that you consider you define a bracket, product of tau ki's. This is the integral over this moduli space of the product. You take, well, the number of this insertion has to be equal to the number of points. So this would be this is included in the notation, and then you put the first Chern class of. So this is a line bundle. The only Chern class it has, it's the first Chern class. So this is this. You put the cotangent line is better because this bundle is more positive than its dual, the curve C, and then you raise it to the power ki. Okay. And you don't need to set, no need to indicate the genus because the genus is found from the dimension constraint. So this is the dimension of M, G, and bar. This is 3G 3G minus 3 plus n, and it has to be equal. So for this integral to be the right dimension, has to be. So this is the complex dimension here. And so this is also the this you can take in principle. This one can take over connected. When I talk about curves, I didn't specify whether I'd like them to be connected or disconnected. It's actually better to think. So if you think about formal properties of various expectation values, it's easier. It's better to think about this one can take connected or disconnected. And the connected ones are more economical, but disconnected ones have better formal properties. And of course they contain the same information, namely the disconnected is the exponential of the connected, and the so disconnected meaning the generating function for disconnected count is the exponential for the connected count. And the reason for the denominators in this exponential formula is because if you have n identical copies of the same object, then in addition to whatever automorphisms it has, so we count these objects, we count this module. So it's a modular space considers curves modular isomorphism, and if you have n identical copies of the same object, so you should get 1 over n factorial, which is 1 over order of the group of the group that permutes this identical copies. So this is when you get there. And so, so this is people consider this sort of things before Witten, but they never realized. I guess one of the main lessons the mathematicians have learned from what not the many mathematicians learned plenty of lessons from theoretical physicists, but one of them is that if you organize your data, if you organize your image of data in an appropriate way, then you may be able to find a lot more. I mean, this kind of data is not, there's a lot of structure, but you have to organize in an appropriate way, and so Witten made this kind of amazing conjecture that if you take, so we will gonna take the bracket will be disconnected. It's not so important, but if I take this, disconnected bracket of the exponential, so this is summation of, maybe call it tau k tk. K goes from 0 to infinity, meaning you expand this out. This will be some function of this variables t1, t2, t4. So this is, he says that this is the tau function of the quartic de Vries hierarchy. And well, I'm sure you heard, all of you heard plenty of narrative about this topic, and you know, I'm not. My goal is maybe not to spend so much time on discussing this particular statement, but of course I should mention that this is related to such giants of modern mathematics as Kontsevich, Mirzakhani, and many other great mathematicians have contributed to this kind of our understanding of this topic. But you can ask, what is it? What is this kind of? Is there some direct enumerative? Is there some kind of direct geometric meaning of this KdV equations? And so then, and maybe so this is another piece of philosophy that I want to share with you. That that if you're not seeing something, if you're not seeing a direct connection between two connected points, but you're not seeing the direct connection, they connected, then maybe they're just two. Maybe this is a degenerate case of something much more general, where the connection is more direct. And in general, so if you're studying an enumerative problem, this will output for you a lot of numbers, and it's always a good sign if the numbers it outputs is not something very, very special, but rather something very, very generic, like falls in the bulk of some other theory. Maybe if you're if you know you're studying an important question, if the answer are related to core objects in some other theory. So if you have two theories that are related, it's great to find some common core, some common generality. I'm repeating myself, but it's very good to have to find a common generality where the kind of the cores of the theory overlaps, not the tentacles of the theories overlap. And so this is from this point of view, the way to think about it is, well, the way I would like to think about it in this lecture is that the KdV equations, well, they're a special case of a lot more general equations. So KdV is a very special case of the KP equation, Kadmos-Petiashvili equations. And then this in turn are a special case of some more general equations, like for example, the two-tode equation. And this is the two-tode is the one I'd like to, that I would like to explain what this equation say. And I will explain it from the point of view from the so again, integrable system for nonlinear integrable equations is a very deep field. A lot of brilliant people worked on it, and like for example, our very own Igor is a giant in that field. And then and the many different points of view there. They have compare and contrast different. They start with slightly different parts of the field. But what I would like to say is that this the work of the kind of the Kyoto school. I apologize. This will somehow takes me a while to move this. And so the Kyoto school says the following. And also Kyoto school is some umbrella way to denote a lot of brilliant people, which I don't want. I mean, probably that's not the place to detail their individual contribution. So this is about the action of the group GL infinity in its Fock module. And the Fock module, the one we've seen, there's a kind of bosonic Fock module, a fermionic Fock module, and this would be the Fock module is the one we'll talk about. It's half infinite wedge of the defining representation. And so we'll discuss what this thing is in a second. But then the corresponding, so we remark the universal developing of GL infinity with this is with central extension. So this is also with central extension. So this is with central. The reason there's a central extension is very basic, is that because what are the matrix elements in acting in a wedge product? They're determinate. And if you're trying to take a determinant of an infinite matrix, it requires a regularization. And whenever you get take a regularization, of a group action, you typically get a central extension. So this is our Yangian, the one we discussed. So this is Yangian of GL1 hat at when the deformation parameter h bar equal to 0. And moreover, the operators, this kind of Nakajima operators, what we discussed. So alpha n's are the become just operators which have ones on some diagonal and 0 otherwise. So so this Nakajima operators are the infinite duplets matrices. And then what is this half infinite wedge? This half infinite wedge, that's actually not irreducible. It has countably many irreducible components, which I can denote like that. So it's summation over n z. You take a vector of the form. Maybe I'll denote vector of the form this is some kind of vacuum of charge n, which also words don't mean anything, but and so you can act. So where this vector n, that is, I mean, just a different color. This is just the wedge product. You start with some basis vector en, and then you go en minus 1, en minus 2, and so on and so forth. Where this is a basis. Of C infinity. And so then if you act by it on by u GL infinity, then you're gonna get so by the rules of your linear algebra, you would know how this algebra acts on the vector like this, and so that would be your decomposition. And also you can write that space. This will be a little bit important. If you want to know if you act on this space, you don't need to act. If you want to generate this whole space, you don't need to act. By all operators. Enough to act by this is actually as a vector space. This is isomorphic. You act by the operators, by the raising operators, alpha minus 1, alpha minus 2, and then apply to this vector n. So this is actually a basis space. And so then as we discussed, then we have the image in general. We talked about the image of the Yangian representation, but in particular the image of GLN infinity. This is cut out by equation. Cut out by equations that if I take an element G tensor G, this will be acting in Fox's space. This commutes with the screening operator. Screening operator at this deformation parameter equals 0. So this would be saying that's an equation, and matrix coefficient of that equation. This is what defines. This would be some quadratic. So this is a quadratic equation on G, or maybe bilinear equation on matrix coefficient on matrix elements of G. And so what that screening operator just becomes the operator summation over I psi I which psi I not which but I tensor psi I adjoint, where psi I is the operator of wedge product by the ith basis vector, and the adjoint is the one that like the odd differentiation. And so this is. So these are, if you think about what this equation say, this some equation for the matrix elements in my semi-infinite wedge are determinants, or doesn't have to be. This is true also finite. This is true also for finite matrices, and this gives you these are just what this thing are. These are Fluke relations. Among minors of G, right? So the matrix elements of G are some minors of G if you're taking a finite exterior product, and then this would be saying some bilinear combination of minors of G that equals 0. So those are Fluke relations. And now this 2 third is the following equation. 2 third. That's not how I spell. This is an equation on a sequence of functions. Maybe write it tau n, and this would be of x and y. that would be, I take the nth vacuum here. I act on, so this would be I act by, so this is slightly, it's always inconvenient in that the operators act from right to left, whereas we write formulas from left to right. So this is act means act by transpose. When we write the formula, you see, we will write the whole formula, you see what it looks like. So here we put a summation of the lowering one. So yeah, put alpha k over k, some coefficient x to the k, and then here I can put an arbitrary matrix G. Here I put the exponential, put the other, so just copy this, what I wrote here. Except I put the raising one, so I put k less than 0, and I give myself other variables, maybe call it yk or y minus k, whatever. And then I still take the matrix element of the vacuum, right? So what will happen here? If I differentiate, take partial. So this is if we have time at the end, we'll talk about why this is called tau function. But this is, so we take partial. Point is not about this. We take partials with respect to x and y. We get all possible matrix elements, right? Because my space is spanned by expression like I get. So the expression like this means raising operator acting in the vacuum. They span my space. So if I get partials, then I get all possible matrix elements of the matrix, of this matrix, this whole matrix. But this matrix is in GL infinity, and so all its possible matrix elements satisfy Pluk relations, and so these are the equations. These are differential equations, part differential equations. Then Pluk relations. This gives it to the equation, partial differential equations. And so where G is an arbitrary matrix, is GL infinity, which you should think about as initial condition. It's like initial condition. And already here you can ask, you would be right to ask the following question: that if you already have the formula, why do we need the differential equation? And this is a valid question, right? So in some sense, when we talk about solvable, integrable system and so on and so forth, then it always suggests some potential of being solved, whereas in reality, very often you already just have the theory gives you a formula. So this is so it's not a solvable, it's solved, and it's not integrable, it's integrated. So that's in some sense that's the formula. In some sense you have the formula. Maybe you don't. You may or may need you may make some use of differential equations, but actually maybe not so clear. And so now what is this? How is this? And this is, we're going to connect. And so this is this. We'll connect. This is, so like I said, this is some differential equation that generalizes Kardashev-Tyashvili equations and the therefore also the KGV equations. And this is seen directly, maybe seen directly. In Gromb-Witten theory of P1. So what's a Gromb-Witten theory of P1 is previously we had if previously we had a curve, we look at MGN bar of P1, it wasn't that moduli space. This is moduli of the following object. So schematically, you now have some curve, and it comes with a map to P1. That is, no, map to P1 is really a rational, in the old language of algebraic geometry, it's a rational function. or map to P1. I apologize. I get a shape like that. So it's P1. And so this is when we talk about rational functions, we very often talk about its zeros and poles. And so in particular, it could be 0, it could be point 0 here, infinity there, and then so this will have some zeros here, some poles. And this map may be constant on some components of my curve F, of my source curve. So for example, I can have a component that is entirely contracted. Maybe be contracted. So that's a possibility. So then these are the zeros, these are the poles. And so in particular, when I have this setup, if talking about zeros and poles, it's a good setup because we can talk about the target being equivariant. So we can make here an action of some. We always denote a variable that rotates P1 by Q, but here, since we're talking about homology, maybe we'll talk about epsilon, which is logarithm Q. This is in the Lie algebra C star that acts on this thing. And so, so then we can talk about products, things like this. You take a product, tau ki. Now we have a marked point. We can specify where that marked point goes. So maybe put it 0. Means these are the sum of my marked points go to 0, and sum of my marked points go to 1 to infinity, and then you get product of maybe Li of infinity. And then this map now has a new degree of freedom, has degree, so maybe has some degree of F. And so we need to, so this is the, we previously had the genus, discrete invariance, and the number of marked points, and this new map has discrete invariance, which is called degree, and so we can put that degree in here. Maybe put some new variable called Q times the degree of F. And then we don't need to specify the genus. Well, we can specify the genus, but they'll be determined by overall constraints. But this is so this is actual dimension of that space. That is so this is a general formula of this is a special case of a general formula for dimension of or maybe I should say the virtual dimension. We'll talk about virtual aspect later in the class. So that is 2G minus. Let me move this guy here and write the normal formula. Virtual dimension of this moduli space. That is 2G plus 2, I apologize, 2g plus 2 degree of f. Just write degree, 2 degree minus 2 plus n. And you can make sense of this expression here by noting that this is just, that would be the number of branch points. So, sorry, this part. I apologize. If I take this number here, that is the number of branch points. Of generic f. So if I have generic map f, it has non-degenerate critical points. Those critical points would be the branch point if you think of this as a branch cover of P1, and this can be assigned independently given local coordinates on the space of maps. And so that's and then n is just number of marked points. Right. So we can talk about this computation. And so this computation, so this would maybe call them out some kind of P1. This guy could compute this on P1. And then there's a formula for this. And we'll make direct contact with Tuitoda, and that's a formula of Rahulpandry-Pandit I. I apologize. So this is the formula says that there's some operators, so you can ask. So that this would be equal to matrix. So this would be a charge. I mean, you can make it charge 0. You can make any charge, but let's say it's 0. I'll write it 0. And then there's some. You think of this as some operators. So and then there's an expression of the following kind. If I remember correctly, it's like this. So exponential of alpha 1, then you put q over u squared. That's the genus variable. And then you take the Fl naught, then exponential of alpha minus 1, and then we put the transpose of this. So this. So you can define the operators in T just transpose of the 1 and 0. Also, this is transpose of that. So put the 0 here. Where for some specific operators, where this TK of 0 are explicit. So first of all, this TK of 0, some explicit matrices. So these are in GL infinity, and they're explicit. They commute. And moreover, they have the form. Moreover, you can write them something of the following kind. You can write this TK of 0 as some operator conjugating some operator, some fixed operator. Well, this explicit depend on the genus. There's a variable that counts the genus. So you take some explicit operator, then there's something like u to the k over, you don't need the k factorial here, but let's put it there anyway. So alpha k plus 1 plus some explicit linear, some explicit linear function of alpha k alpha 1 inverse. So of course this commute, the alphas commute, and so then if you conjugate, you're going to get commuting operators, and where this is also explicit. And upper triangle, explicit and triangle. And so since it's triangular, we can just conjugate. So this would be saying this expression we can write as 0, then kind of Toda times, and then we get W inverse whatever W, and then again Toda times, and then 0. And so that says this function satisfies the two Toda equations, and with some change of time. So this would be a linear change of times, right? So there's some function of ti's, or whatever xi's and yi's, and there's some linear change of this variable that this makes a solution. And moreover, you can really think of this. It's not the whole. It's not like this, the formula equals formula. It's really pieces of the formula equal pieces of the formula. So this is maybe something I'd like to stress, and that so this is you should really think of this as kind of a target space. So.
Sorry, may I ask about this formula?
Sure.
You write here that tau k is dependent. You take it at 0, yes? So it have to be defined somewhere in some way outside of 0.
No, that's just at 0 means your marked point maps to 0.
Ah, I see.
In principle, marked point can map anywhere you like, but it means this is.
So it depends on you, yes?
Depends on you, right? Depends on.
Okay.
Depends on you. Yeah.
And when you write genus below Q over U squared,
this means right. So this means okay. Maybe I'll put it here. So let me.
You mean that it counts genus, yes?
I mean the following. So here we put some variable u that put 2 minus 2g, or 2g minus 2. Sorry. 2g minus 2. So in particular, this is 1 over u square comes 1 over u square comes from just the counting, just the sphere itself has genus 0. So the sphere itself comes with with weight u 1 over u square, and so that's this 1 over u square here. So suppose there's nothing. You're talking about just maps that are just maps of bunch of p1s to p1, and they're just bunch of maps mapping identical to p1. And this curve, if you have d of these components, then the genus of that, then the combined Euler characteristic of that would be minus 2d. This minus 2d this is L. It comes from this L naught and in u square. So the combined Euler characteristic would be u to the minus 2d, and this comes from this.
Mm-hmm. And the number of marked point is equal to number of terms in the product.
Exactly.
Yes?
Yeah. Right. And so what I'd like to say is that once you I really like when there is some kind of target space point of view, maybe target space point of view. Is that when we have we had our P1, but now what I'd like to say, maybe I'd like to draw it instead of vertical, I draw it horizontally. So this is my P1, and it had 0 and infinity. But now I'd like to think about my theory in the target space, right? That's after all that's a legitimate point of view. And in particular, I can take my target space and I can, like for example, I can cut it. So these are really two halves. So the two halves of the formula come from maps to so especially if you're doing localization, then it really is the case that the two sides of the localization formula come. So okay, maybe there's some physical space. Maybe Fock space is really the space of state. My Fock space is the space of states. Over that cut. And generally, if I have some theory in the target, it's going to be a topological theory, and it has some space, and that's over that cut here. Namely, if I think about that cut, then over it might have some curve mapping that there, and over that sorry, I didn't want to change the color. If I have some curve mapping there, that what would it look like? So it was some some kind of curve. I draw it like that, and it maps to my P1. Remove this. Make it so this projects to my P1, and then what the topological data I'd like to recover is how many times each of the circles cover the circle downstairs. So maybe I'll put them in a different color. So maybe this circle covers this 2 to 1, and that other circle covers it maybe 3 to 1. So I get over my space of states here is going to be a partition 2, 3, 2. Which is a partition of the number degree. Right. So the total degree of the map is how many however many loops I'm going to get in the pre-image, and the total winding of them has to give me the degree. And so this is my space of state is quite literally the space by partitions of the number d. Does that make sense? And so then in particular if I take d copies, if I have d copies of my disk, this is what I was trying to say before. that in particular should get a weight, which is this just should get a weight. Total degree is d, and the total order characteristic is minus 2d. So this would be u to the minus 2d, and this is recorded by this operator q over u squared to the degree to the L naught. And so this is what this guy got. And in general, if you think about the how to compute the genus using this kind of covering argument, you see that this is the right, so this is square here. That's the right multiple to have. And so this is saying that what I'm trying to say that it's really the case that this operator which I have on one side let's see if it's gonna work for me like that. Okay, super. So if I just erase 1/2 of this, 1/2 of this is the operator. It's this operator. Okay.
So this is not a vector. This is operator.
This is, well, I mean, this is right. This is that on one side it's matrix element. Sorry, true. That is correct. So this is like this is a vector, right? Like that. So so this is in particular this on the Gromb-Witten side. This says this is a formula. These are some kind of Hodge integrals here. On Gromb-Witten side. And this is given by this. Right? So it's so the fact that you get the sort of setup, the setup in which we describe the two-order theory is really in the native setup of Gromb-Witten theory here for P1. And then I'd like to maybe say one word about you can take so this is this was all in a covariant theory, in non-covariant theory. So this is some limit. Limit a certain limit. And that limit, it's described by the usual Toda. So in the non-recurrent limit, you instead of getting the infinity, so if you forget the covariance, infinity and 0 are the same point. So this is you get for some kind of tau k of a point plus, and then you get plus this Dubrovin-Jung. Equation for tau k of 1, where 1 on P1, where 1 is the limit of 0 minus infinity over epsilon. Right. So this is, if you have in a non-covariant theory, the cohomology is a 1 and a point, and then 1 is a certain limit of the two combinations. And let's focus on this first part. The first part you can write. So here you can write something much more basic. You can write. So here, if I want to, so here. this formula here, we want a product of tau k over point, tau ki over point. And let's have it as before. We have q to the degree u to the Euler characteristic, and this is a vacuum matrix element of. You can put these operators here now here, and here you get some diagonal matrices. So in G infinity, q to the L naught q over u. Sorry. Maybe I shouldn't be stressing this. So if you're interested in if you're interested in operators, like, so where I'm driving here. So in general, in non-occurring theory, we also have an operator which is like a tube. Means you have right. So then here you can put this your point. And so then you get, so then this would be an operator. So if I have so this is my point, and here I can put the case descendant of that point, and this is an operator now. It's an operator in Fock space, but in fact an operator in Fock. And this of course, this on general grounds, this commute, because it's topological theory. In topological theory, order of insertions doesn't matter. So this commute. Commute, but then it's this is like a quantum integral system, but this is really well, it's not a very complicated one. These are just diagonal matrices. So G infinity. And to connect it to the quantum system we saw last time, or I guess we didn't have so much time to talk about it. I hope you watched the video. Well, if you didn't, but anyway, there's some. We did talk a little bit about it. To connect it to the quantum integral system, this is like the very degenerate case of this kind of Baxter. This is a degenerate case from commutative subalgebra. In the Yangian of GL1 hat of Baxter type. We can talk. So the discussion from a week ago, there was this: once we have an R matrices, then you can get some commuting elements, and then these commuting elements, you can ask for what's the geometric meaning. And the very degenerate case we see here is that when you take the whole Yangian collapses to just GL infinity, the commuting operator is just diagonal matrices, and then you get those are the operators of those are insertions in here. So also I want to say something again slightly philosophical, that if you take this matrix element here, maybe I'll copy it here. And so then by definition, what's it going to look like? So this would be a sum over, so this is some matrix element in the Fock space. We start with vacuum, we create something by, so this creates, this kind of, this creates partition. So the diagonal matrix elements, they diagonal in some basis indexed by partition. In fact, if you think about it, those are just monomials, badges of monomials, or in the language of alphas, those are the Schur functions. And so then these are diagonal. These guys are diagonal. In pure wedges, also the same as the Schur functions. And so this is what was going to be like. This would be summation over all these partitions. And then when you create a partition from this, you're going to get, when you create a partition, you're going to get something like the dimension of the corresponding representation of symmetric group squared. These are dimension over the size of lambda. And then since you create an annihilate, you're going to get the square of that. So this is from creation and annihilation. And annihilation. And then you're going to get an action of diagonal matrices, means you have some polynomial. You're going to get symmetric times symmetric polynomial. Specific one, but let's not be too concrete. Polynomial in the lambda i's minus I, because those are this is how it acts. And so this is, you think about it, this is just a finite analog. This really is. This is really a finite analog. Of the, you integrate over matrix of the kind of GOE integral you get, like kind of summation over x in Rn, and then the first analog is a product of xi minus xj square. That's this. If you write the formula for dimension, it's going to look like this, and then some polynomial of x, and then this maybe. So this is also some exponential minus x. So this is really some kind of multinomial coefficient. Multinomial coefficient square, and so this would be its limit would be there's the summation of xi squared, that sort of thing. And so if you like this sort of expressions and you think they're deeply connected to various problems in numerative theory, maybe one point of view to see it about them is that there really is just continuous limits of things which are not somehow not the things that are connected not not figuratively, but very, very directly. I mean, just really by definition. Well, right. And so, then you can ask, well, where is the kind of questions? So then, natural to ask. Maybe. Sorry, these are what's the word? Rhetorical questions. I didn't prepare a list of rhetorical questions. But the list of rhetorical, maybe there is a. There are deeper reasons. two partitions here. And then also, what about h bar not equal to 0, right? I.e., the whole Yangian. And the Yangian is full Gordon. All right. So, and of course, the answer is yes. Sorry, these are not yes/no questions, but the answer to both of them is yes. And then, and look, the answer is of course found in, because most of you know. So the answer is found in Gromov-Witten equals DT theory of local curves in threefold. So instead of having, so this is, what is this about? So I had, so in principle, so once you did P1, you can do any curve. So this is also done by Rahul and I, and involves the same, roughly the same data. And so then you had, so maybe I'll draw some, I had some target. This was target curve. This is, it's not the source curves. When I was drawing curves before, I meant it to be a source of a map. This is a target. And then what you can do is you can promote it to being a threefold, which is some kind of formal neighborhood of this curve in some threefold. So meaning can so instead of curve, it's going to be threefold. And then you make this a threefold by taking two total space of two line bundles. Threefold X, so maybe there's like a line bundle I2, which is the total space of one line 2, or my curve C. Maybe since it's a kind of a base curve, maybe I'll call it B. Call it B here, and that's my threefold X. And since I have a space of two line bundles, so if, in principle, I can have some vector bundle, but any vector bundle, Gromov-Witten theory is a theory, or also intuitive theory we study, they're deformation invariant. And so if I have any vector bundle, I can break it up into two line bundles. So I might as well do that. And then it gets two more automorphism, namely maybe call it T1 plus T2 and T2 that scales that. And why is this a generalization? Is because, well, in general, anytime you take a vector bundle of variety, then the theory of the vector bundle recovers the variety in some limit. But here it's just the passage back is very easy. Is that if you go back here, that if L2 is L1 dual, and so in particular T2 equals T1, or maybe if I write additively with D minus T1, then by Mumford's relation you just recover back here. There's some relation that say that if if the two bundles you have is one is dual to another, then you just can forget about it. There's nothing happening there. And so there's a it is a special case, and this is, we know that this combination, or combination H bar, that was really is minus T1 minus T2, and so this makes sense that if that set, that combination is precisely well the way, anyway, it's proportional to in some definitions that. So then this is so that is the different, so the parameter that by Mumford relation reduces you back to from a threefold gives you a curve. That's exactly so this would be the theory where you have here we'll have the general Yangian. And here we have the GL infinity. That's the specialization. Meaning that the operators that we consider here, for instance, this guy, this sort of operators, point, this would be this Baxter subalgebra. And the Baxter subalgebra had a parameter, and that parameter is like had Z with Z was I think the way we define this without the minus, so exponential IU. So otherwise, it's everything exactly the same. Then you can ask about this cap here. Move it here. So this is so Mikola asked whether this is a vector or an operator, and this depends on your point of view, because if you think about this is kind of like this is a vector that depends on a whole bunch of variables, right? So you can, in principle, here you can stick things like kind of exponential of a summation like tau k of 0 tk, this sort of thing. And so this is like an operator between Fock space and polynomials in some. So this is, you think of this as it's either a vector in Fock space or it's an operator between Fock space. It's a vector. It's either a vector of fixed Fock space that depends on infinitely many variables, or an operator from Fock space. You can think of this as an operator between functions, between kind of polynomials in tau k of 0. This goes to Fock space. So in some sense, it's kind of infinity. So right. So this is a map like that. And so that is understood in terms, again, this is also understood in terms of some polynomials and insertion. So this has to do. This is also understood in the Yangian chain, so we'll explain it later. So this is understood. Same terms. We'll explain later in the course. And now about partitions. So partitions, of course, come from the. So I was thinking about kind of Gromov-Witten side of things, but in 3 dimensions, in general, Gromov-Witten theory is equal to Donaldson-Thomas theory. Donaldson-Thomas theory is some enumerative theory of sheaves. So Donaldson-Thomas theory. This is enumerative. Sheaves on threefolds. And also, you can say, well, no subjects in related categories. Right. Sheaves on a threefold, it's a coherent sheaves on a threefold is a very nice category. When a smooth threefold, it's a very nice category with a lot of properties. And there are other categories which you can study, which just look very similar to that, and you can study those. It's like, and so, so if I have a sheaf on a threefold of the kind as I considered, so maybe, so if I have you have a sheaf that maps, you have a threefold that fibers in some surfaces. So I have a threefold. So X X that fibers over some base in some surfaces S. Then the sheaf on X is like, so a sheaf on X it's like a map from the space B to modular F sheaf on S. Right. I mean, it's really is a map if you have, it's really a map. So what by definition, when you talk about modular F sheaves, what's a map to modular F sheaves? Map to modular F sheaves is some sheaf on some ambient family. It's really a map. If flat B. But we don't want that. We just take them all. So if something is not flat, that means it's otherwise with some map with some singularity. What is a map with singularities? And the singularities we like because it's they're going to be there anyway, right? Because if even we talk about this kind of Gromov-Witten theory problem, it's not the case that the all moduli spaces, all points in my moduli spaces correspond to a nice map from a nice. So when I had this picture here, this picture here, if I talk about Gromov-Witten moduli spaces, then there are points in them that correspond with, for example, for where the domain of the map has to degenerate. And so this is here. B is a target space. B doesn't degenerate, but instead we get some singularities, and this is in fact this works better. For many aspects, this works better than the than this kind of Gromov-Witten type of quantification. This is, in some sense, these singularities are more desirable than the singularities we get in Gromov-Witten moduli space. Well, at least kind of from my point of view. Again, what's desirable, what's not desirable is strictly personal. You may like other singularities. I like the singularities better. And so then there's so maybe a picture. Let's copy this picture from here, which I so see if I can like this picture, which you see is here's a here's a picture of a monomial ideal and the corresponding sheaf. So here's a picture of that picture here. That is a monomial ideal. Ideal sheaf really on you take O of -1 plus O of -1 over P1. And so this corresponds, so this has degree 2. The way it's drawn has degree 2. Over P1. And so corresponds to a map to kind of map the singularities P1 going to the Hilbert scheme of the fiber, Hilbert scheme of C2 2 and then this is and in fact over an open set outside of 0 and infinity, it just goes to just one particular configuration, which I'm going to draw like that. So the way it's drawn on the board, there is something like that, meaning, so these are my two squares, and this means ideal generated by maybe if this is x1 squared in x2. So that's okay. But over 0 infinity, you get some stuff, stuff we like. Stuff is good. So otherwise, in somehow this should be compared and contrasted with the situation with in the Gromov-Witten theory. In the Gromov-Witten theory, we would have kind of a typical situation in Gromov-Witten theory that we would have this is my base P1. And then I can map to that maybe 2 copies of this P1, maybe identically. color. And then, but then here, over my special point, I can have an arbitrary curve of arbitrary genus. I'll collapse to that point, and I will have to worry about that. And then I just maybe over this point, I can have some other genus. That sort of thing. Okay. So that's the Gram-Witten analog of the situation. So instead of summing over, you have to integrate over these things. You have to compute here. You're going to get these Hodge integrals. Over this, integrate over the moduli of that, and whereas on the other hand, you just can't kind of use it. Here you get box counting. These Hodge integrals, they become equivalent to box counting, which is especially simple for so-called Pandey Thomas counts. But anyway, whatever you think when either of them, both of them, as we discussed, they both, you don't have to do those counts, both solve explicitly. Using quantum groups, or maybe in the language of quantum groups. Okay. All right. So now we come to the most interesting part of the talk, which is with 1 minute to go. It's the best time to start it. Is that this was about so far we discussed Yangians. So what about other quantum groups? All right. So where would they appear? And so this is I mean, I'm sure if you're following this course, you know perfectly well what to expect. Is that if I'd like e.g., if I'd like UQ of GL1 hat, that should has to do with now K theory of DT moduli stasis. And this is now for local curves, for X local curve. And so what does it mean to study K theory? K theory we usually study in a situation, what is not usually, but the way I explained in the very first lecture, if you remember anything from back from that time, I certainly remember very little, is that if you, instead of thinking this base curve here, from this, you should go to you should think of this. These are now, so K-theory has to do with some space of states and some geometry like that. And so it means you now have to promote yourself to the situation when you have some time direction, and in particular compute the index means you compute the time, the partition function with, you have to add a circle of time. So instead of, if you think about the sort of target space theories, so previously we had, we were talking about, we were thinking everything in terms of the base curve B. So we can somehow, our curve B is promoted to B cross maybe S1. So that's now threefold. And this is the world volume of a membrane of M2 brane. Of M theory. So I'm not going to talk about, there's no time left to talk about M theory, but it is some 11-dimensional theory in which has extended degrees of freedom, and one of them, the M5 brane and M2 brane. We're not going to touch M5 brane in this course just because I have nothing to say, nothing meaningful to say about it. But M2 brane, you can take of the form, Riemann surface cross S1. And then if you want to compute in that theory, in the Hamiltonian approach in that theory, you'd be dealing with K theory of some moduli of objects on the B. And so then the theory, the theory was this theory we're talking about, the UQ GL1 hat theory is the theory of a stack and two branes on this geometry inside some ambient 11 inside some ambient geometry, which has to be 11-dimensional. So I would say Calabi-Yau 5-fold cross S1, this kind of S1 times. And how many M2 branes stack? So this how the number of membranes that's the degree, that's the analog of the degree of the map. So the number, the operator, the number of membranes, that's just L naught. It's a degree operator. Okay. And so that in general, you can think about many. You can imagine there are many somehow. In general, some maybe the main, maybe one of the the many motivations to study two plus one dimensional theories, like we do in this course. It is to better understand. And two branes. can say I made some statement here, but that statement is a mixture of conjectures, and I mean, it's a mixture of some conjectures and some things I can prove. I mean, the main conjecture is not even a conjecture. It's there's the actual moduli space of supersymmetric state of membranes. That's a space under construction, and so like if this is some of you like Yasha know very well, that's a space which has some aspects of that needs to be clarified. And so this is, anyway, that's a subject full of mysteries, and to better understand these mysteries I find it's useful to study general properties of 2+1 dimensional theories of the kind we talk about in this course. Right, so this is, I'm now a whole 7 minutes over time. Maybe I'll take some questions and then we conclude.
Sorry, I got again a computational question, and in case of H-deformed case in full Yangian, centrally extended, what replaces Plücker relations and KP integrability? Or it's
that's the screening operators we talked about. So last time we talked about so this is maybe so screening. This is the screening, or maybe I'll put, so okay, maybe we'll put it, I'll make it to, I'll put it to the right place in the note. So Plücker relations, they're a special case of screening operators. And screening operators, as we discussed last time, they come from just literally slices. There's a very clear geometric meaning why they are there, and so then they still exist, and your quantum group still commutes with all of them. So those are things that replace. I mean, this is you should think the screening operators. They're screening operators. They something specific about this quantum group, kind of GL1 hat. But slices exist in general for any quantum group that we consider. There's slices, and they give relations absolutely general. And this was the subject of the lecture last time.
I'm sorry. In which sense a relation corresponds to an operator? Like Plücker relation corresponds to a screening operator.
Well, relations for quantum groups are what? Relations for quantum groups are the operators that commute. So you have a quantum group that has some representation, has the tensor products of representation, and every relation, this is, maybe we discussed that in like lecture number 3 or 4, something like that. Every relation in quantum group means you have some operator that commutes with the action of your quantum group in a bunch of, so maybe I'll talk about that like this. So suppose you have if I write a representation of a quantum group as some maybe some collection of arrows, like there were V1, V2, and so forth, V whatever n, and then there's some kind of quantum group operator, which you can think about it as maybe matrix coefficients of an R matrix, but that's how it acts in the This is how it acts in some representation, and this picture really literal for vertex model, but otherwise it's also very convenient. And then suppose you have some operator, some kind of intertwiner, and then it goes to some different connection. So sorry, just too early. It goes to some different relation. V1 prime, V2 prime, so on. Okay. And so what the intertwiner means that if I take this matrix element, then this is equal to the same thing if I put it here. Okay. This is what it means. But now if you think about it, if you read it the other way, this would be saying this would be saying that some, if you exchange the role, so this as an operator intertwiner, psi maybe called psi, and so psi commute. That's my quantum group. And so now, if we interchange the role of what's physical space and what's auxiliary space, so if we interchange the role of that, if instead we think about this direction being the physical space and this direction being the auxiliary space, then this gives a relation in quantum group. Okay.
Am I understand right that you say that this operator omega, which is psi I times psi I star, is replaced by full Newton-Tonic matrix, like an operator?
No. The screening intertwines. Like the actual Virasoro screening intertwines the instantaneous matrix. That intertwines. That just intertwines GL infinity. You have to have. If you want the so if you have this, you want a intertwiner for the Yang between Fock times Fock going to Fock times Fock, then you need an actual Virasoro screening operator there.
Okay, and one more question about tau. You defined tau operators, and you said that there is some linear replacement of variables, that some linear combination conjugated by double, and this linear combination doesn't preserve gradient by energy of fermions. Yes, so this is linear combination is psi 1 plus psi 2 plus psi, alpha 1 plus alpha 2 plus alpha 3.
Right, it doesn't preserve. Yeah, exactly. Yeah.
Okay. This is not a usual thing. Okay.
But it's given by some. It's something very, very natural if you think. This is that change of variables. It's anyway. It also comes. So you can ask the following question: like, suppose I actually want an explicit map between the Gromov-Witten descendants and Dons and Thomas descendants, and that sort of change from Gromov-Witten descendants to Dons and Thomas descendants, that will have that same feature. Well, I guess it has to, because right, there'll be this feature there. That sort of change. I mean, that change of variable is related to the change of variables between the Gromov-Witten Dons and Thomas descendants.
And probably I missed his answer, but what replaces 2 toward the equation for finite H bar?
I'm not sure. I don't think this is. It's not. Yeah, you can sit. I mean, you can write it down, but I'm not sure if it has some name.
But is this a differential equation or difference, or
you can? Well, it depends how you. It depends how you the actual that cap. That cap here. That has to do. This has to do with this is understood in ways. We'll talk about this. This has to do with. Has to do with solving. Solving the quantum differential equation. and in particular, it has to do with you can. Yeah, I'm not. Yeah, I honestly didn't think about this. I think it's so maybe the way to answer, to explain maybe my point of view on this, maybe I'll repeat it. So the point of view of this of Kyoto School, I mean, okay, sorry, this would be a silly summary of deep work by many people. They've noted that if you take this statement here, that you have what was that statement here? That's this statement we're looking here. So what does it say? It says you have a quantum integrable system. You have a quantum integrable system with kind of really big non-abelian symmetry of an action of some big group by symmetry of some vector space, and you compute in that quantum system, you compute some generating function for expectation of certain observables, and those observables commute among themselves. So this is you have some operators in your group, so they're like these operators commute among themselves, and these operators commute among themselves, and so you have a way to produce you have a theory with some very strong quantum integrability, and you make a function out of it by taking biochromatic elements or traces of elements where you stick commuting families of operators. And then maybe a general philosophy of more general philosophy of Kyoto School that I stated here is that those objects they typically satisfy. Now that's what we started with, a quantum integrable system, and you go to a classical integrable system. You get some function that satisfies some classical integrable equation. And so, that's a marvelous, it's a marvelous direction, which somebody should explore. But right now we're at the stage where we understand the quantum integrability really well, and so we focus on that. So maybe more fundamental object. You understand the quantum integrability of the problem in the sense that you have some, you have some space, some operators, some commuting families of operators, which we can name, and then you can then investigate the question of if I now convert this data into functions, what sort of classical integrability of the corresponding functions will the quantum integrability imply? That's a legitimate question, which I don't think I have an answer for that. I mean, certainly not. I didn't prepare one today. So what I was trying to say is that kind of not unlike the point of view of the Kyoto School, geometrically you can unravel the deeper quantum integrability, which will be kind of some object which is deeper than the classical integrability, deeper than just the integrability of the KdV equations.
Okay, thank you.
More questions?
Yeah, this is kind of unrelated, but Nekrasov and others on sheaves and fourfolds and DT theory of fourfolds, does that also fit into this M theory picture?
It's eventually it should, like it has to have, like if I have like a Calabi-Yau fourfold closed elliptic curve, and I'm asking for M2 branes that are set on this or wrapping that elliptic curve, then I should get a theory which is like like Nekrasov theory or Hilbert's scheme or Hilbert's scheme of points on fourfold. That there should be, I think, more or less, like if you take M theory of the like Calabi-Yau 4 closed elliptic curve, you should get that theory, that later theory. But not the general sheaf. In M theory we have the membrane and we have the 5-brane. I don't know, and I already said many times, every time I bring up the 5-brane, I say I know nothing, very little about it, so I just mention its existence.
And is there a reason why you say this fourfolds cross an elliptic curve rather than C or something?
we don't know much about M theory for membranes which are not compact. So that's another issue. We that modular space of membranes that Yasha likes and many other people like, which is, like I said, there's a space under construction. Right now, it works well for compact membranes. So if we have something non-compact, then this is subject of current research. More questions? All right, then next time, so we'll start with the foundations of unitive geometry. Like, for example, I say integrate, I say count, and so on and so forth. But underlying all of that is the notion of the virtual structure shears, virtual fundamental cycles. And we're very, very fortunate that next time we have the best possible expert talk about this topic in a class. It will be Melissa. We'll speak next time on all this very important notions. So that's all for today. Thank you so much.
Thank you.